The Friedel-Crafts Acylation is an electrophilic aromatic substitution, or EAS reaction. In EAS reactions, a proton on an aromatic ring is replaced by a potent electrophile. And in all EAS reactions, the aromatic ring acts as a nucleophile. Specifically, in Friedel-Crafts acylation, an acyl group is installed on the ring. The reaction requires an acid chloride and aluminum trichloride, and the product is an acyl benzene derivative. Much like Friedel-Crafts alkylation, the mechanism begins with the Lewis acid-base reaction. But this time, that Lewis acid-base reaction is between an acid chloride and aluminum trichloride, and it results in the formation of this Lewis acid-base complex. The subsequent dissociation of aluminum tetrachloride generates a cation known as the acylium ion. The acylium ion is stabilized by resonance that delocalizes the positive charge onto the oxygen atom. And the acylium ion will serve as the potent electrophile in this EAS reaction. A pi bond of the benzene ring now attacks the acylium ion. This results in the formation of a new sigma bond in the intermediate known as the sigma complex. And this sigma complex has the typical resonance forms encountered in EAS reactions, which delocalize the charge to two other locations on the ring. The reaction concludes when chloride dissociates from aluminum tetrachloride and removes a proton from the only ring carbon that is sp3 hybridized. The loss of this proton restores aromaticity to the ring and yields the acyl benzene product along with hydrochloric acid, and it regenerates the aluminum trichloride catalyst. Let's now turn our attention to a specific example with regiochemical considerations. Bromobenzene can undergo Friedel-Crafts acylation with propionyl chloride and aluminum trichloride. In this reaction, the para and ortho products are produced. The mechanism begins with Lewis acid-base reaction between the acid chloride and aluminum trichloride. The subsequent dissociation of aluminum tetrachloride from the Lewis acid-base complex results in the formation of an acylium ion. Rearrangement is not a concern here because the carbocation is resonance stabilized by the adjacent oxygen, and if that carbocation were to rearrange, it would lose that valuable resonance stabilization. The attack of a pi bond of bromobenzene on this electrophile could place the acyl group in the ortho, meta, or para position. Since the ortho and para pathways are electronically equivalent, we need only draw one mechanism. Let's consider the attack of a pi bond of bromobenzene on the acylium ion to generate a para-substituted sigma complex. The para-sigma complex has not only the usual three resonance forms that move the charge to new locations on the ring, but it also has an additional resonance structure in which bromine donates electron density to move the charge outside the ring. This additional resonance form is particularly stabilizing because all of the atoms in this resonance structure possess a complete octet. this point, it is worth pausing to note that the halogens are a bit of an anomaly. The halogens deactivate the ring toward EAS reaction by inductively withdrawing electron density from the ring. Most groups that withdraw electron density from the ring and therefore deactivate it towards EAS also direct further substitution to the meta position. However, the halogens are unique in that they are deactivating toward EAS but direct further substitution ortho and para. The mechanism concludes with the loss of a proton to a chloride that dissociates from aluminum tetrachloride. The proton is lost from the only ring carbon that is sp3 hybridized, and as those electrons collapse into the ring, aromaticity is restored. In this case, the para-substituted product results. The ortho product is formed through an analogous mechanism. If we compare the meta pathway, we will see why it is not favored for this reaction. So now, let's turn our attention to the attack of a pi bond of bromobenzene on the acylium ion to generate that meta-substituted sigma complex. This sigma complex also has the 3 expected resonance forms for any sigma complex in an EAS reaction. These 3 resonance forms move the positive charge to different locations around the ring. However, there is no opportunity for the halogen to participate in delocalization of the charge. Consequently, this sigma complex is higher in energy than that found in the ortho-para pathway. And that's why the meta pathway is disfavored for this particular reaction. The Friedel-Crafts acylation has some limitations, and those are the same limitations that we saw in the video on Friedel-Crafts alkylation, so you may find it useful to review that video. In short, the reaction fails with rings bearing nitro or amino groups. Additionally, rings bearing carbonyls or similar groups conjugated to the ring are also unreactive. And this includes aldehydes, ketones, acids, amides, esters, and the similar nitriles. The ketones of acylbenzenes formed in Friedel-Crafts acylation reactions can be reduced by one of 2 complementary reactions. The first is known as the Clemmensen Reduction, and it utilizes a zinc-mercury amalgam and HCl. The second is the Wolff-Kishner Reduction, and it utilizes hydrazine and hydroxide. Either of these reactions will reduce the carbonyl of an acylbenzene to a CH2 or methylene group. Notice that this series of 2 reactions, namely Friedel-Crafts acylation followed by reduction, provides a solution to a problem that we saw in the video on Friedel-Crafts alkylation. And that problem was the inability to prepare propylbenzene. We could not prepare propylbenzene from Friedel-Crafts alkylation due to carbocation rearrangement. However, as we noted earlier in this video, Friedel-Crafts acylation is not subject to rearrangement. Consequently, primary carbons can be added to the ring by Friedel-Crafts acylation. If the carbonyl is then reduced, the net result is the installation of a primary alkyl group onto the aromatic ring. In summary, Friedel-Crafts acylation is an EAS reaction that replaces a proton on an aromatic ring with an acyl group. When the reactant has a substituent on the ring, the relative stabilities of the sigma complexes determine whether ortho and para or meta products will be favored. The preceding was an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.